Welcome back to Second Collisions, the final day in this amazing online event. We have an action-packed afternoon, which includes talks from some highly impactful CERN alumni here in the main auditorium. We have networking sessions in Restaurant 1, an entrepreneurship workshop in Idea Square, but now it gives me great pleasure to introduce you to our moderator and Second Collisions organising committee member, Connie Potter.
o'clock last night watching Double Negative.
Hey Connie, how are you doing?
I'm doing good, thank you. I was here last night till the very end watching Double Negative's fabulous talk. Oliver James gave a really interesting talk, and tonight I'm going to see one of their latest films, Dune, at the cinema.
Oh, they did that. But did you know that they're actually recruiting CERN alumni?
I heard him mention that. What an opportunity. It's incredible.
Yeah, who wouldn't want to work for Double Negative? I still like working for CERN though. Anyway, who have we got coming up next?
So coming up now, we have Suzie Sheehy. She is, one moment please. Right. I met Suzie for the first time for a coffee a few days ago. Neither the 30-minute coffee nor the 20-minute talk she'll now give is enough to learn even a fraction of what she's achieved so far in her career. A native Australian, she divides her time between her work on high-power hadron accelerators at Oxford University and her group focusing on medical applications for accelerators at Melbourne University. Could you get further apart? She's also founded the Accelerate outreach programme in the UK and incredibly has found the time to write a book, The Matter of Everything, due out early next year. While reading through the comments on Suzie's Royal Institution talk on particle accelerators, in amongst the marriage proposals, I found one that said, wow, impressive, very impressive. I look forward to reading about what Miss Sheehy discovers and creates over the next decade and more. As do I. Don't forget to put your questions in the chat. Over to you, Sheehy.
Thank you, Connie, and thank you for the wonderful introduction. I hope everything is working well here, and I'll just wait for the slides to come up as well. So in today's talk, I was asked to talk about both my career in accelerator physics and also science communication. And a lot of my communication nowadays is around this idea of curiosity-driven research. And in preparing this talk today for you, for CERN alumni, I thought, well, what can I say to these people that they might not have thought about already? And actually, just this morning, I came across a wonderful article by the science writer Ed Yong. And he was reflecting on, and the article is called, if you would like to read it, How the Pandemic Changed How I Think About Science Writing. And in it, he had this quote, which I really loved. And so I want to start with that and then build from there. He says, science is often caricatured as a purely empirical and objective pursuit. But in reality, a scientist's interpretation of the world is influenced by the data she collects, which are influenced by the experiments she designs, which are influenced by the questions she thinks to ask, which are influenced by her identity, her values, her predecessors, and her imagination. And I thought that was a really great place to start for the story I'm going to tell you today about how my science and my science communication have over the years empowered each other, and how that is true throughout the history of my field, not just for me personally. So I want to start back in 1927 with this guy, Ernest Rutherford, a fellow Antipodean. He was from New Zealand. And he came to the UK, actually on the same fellowship that I had early in my career. And obviously Rutherford had achieved a lot by 1927. He was already well established in the field of radioactivity, but he was growing increasingly frustrated with the types of experiments that he was carrying out to try and understand the atom. By this point, they discovered that the atom had a tiny nucleus through the gold foil experiment in 1909, and he developed his atomic model in 1911. But he still didn't really understand what was inside the atom. And so in 1927, he was now the president of the Royal Society, and he stood up in front of the great and good of the scientific elite of Britain. And he said, "It's long been my ambition to have available for study a copious supply of atoms and electrons which have an individual energy far transcending that alpha and beta particles from radioactive bodies." His problem was that natural radioactive substances like radium could only reach a certain energy in the radiation that they emitted, or the alpha particles they emitted for his experiments. And they headed out in every direction, and they declined over time with the half-life, right? So doing controlled experiments with a high data rate was very, very difficult in 1927 and involved many long hours sitting in a dark room with a microscope looking for tiny flashes on a scintillating screen. That's literally how this science was done. So Ernest Rutherford in this call was really asking for the first particle accelerator, and he wasn't the only one actually who was working on this. And in fact, it was his people, Cockcroft and Walton, of course, who built the first accelerator, which I'll talk about in a second. But they had competitors all over the world, actually. In the US, there were people using giant Tesla coils to try and build up a high voltage through which to put particles in order to give them energy. There were even some researchers in Germany who strung enormous cables across a big gorge and waited for the lightning to come through. And they actually successfully managed to harness about 15 million volts for their experiments. Of course, they didn't build an accelerator with it, but just as they moved up to trying to harness 30 million volts, one of the experimenters died in an accident on the mountain, and that was the end of their adventurous type of particle accelerator made from lightning. So obviously it was a little bit safer, but not much safer to try and do this in the laboratory. And that's what John Cockcroft and Ernest Walton, who was just a student at the time, actually did. They built this machine that you can see on the right-hand side of the slide here, which was the first working particle accelerator with which they split the atom in 1932. So this gave them not just new results, not just new science, but it gave them a new ability to investigate the fundamental matter of our universe through this technology. Now, most of you have probably heard of that story of Cockcroft and Walton and the first accelerator, and you can see Walton there sitting underneath the beam tube. Now, just an extremely dangerous thing to do, but they would actually sit underneath there and look for the flashes on a screen from the decays as a scintillating screen lit up. And actually, when they made the first experiments on end of April 1932, Walton wasn't sure of what he was seeing, and so he grabbed Rutherford and bundled this 6'4" guy, Rutherford, into this tiny box with his knees up around his ears. And Rutherford successfully confirmed that they really were seeing alpha particles, and that was their indication that they'd managed to split the atom. All right, if I can get this thing working, let's go to the... There we go. So what you might not have heard of is then another story about the invention of particle accelerators that happened around World War II. And in fact, just before World War II, these two brothers, Russ and Sigurd Varian, and some of you will recognize the name Varian, were living in a socialist theosophist community called Halcyon on the Californian coast. And they, along with many other people, were interested in how to create radar, how to create a system which could guide or detect enemy aircraft, because of and this went on into wartime, right? So it was a very difficult challenge. And they tried building a lab in their small community, but they were having lots of difficulty doing that. And so they hooked up with someone up the road at Stanford named Bill Hansen, and he's the one in the right-hand side on that middle picture there with the glasses and the fantastic eyebrows. And Bill was actually interested in developing particle accelerators. And what he came up with was what he called the rumbatron, which was a sort of cavity-shaped device in which electromagnetic waves bounced around in such a way that they might be able to amplify and accelerate a particle. And so at the start of World War II, while the British were working on devices called magnetrons, which gave out radio frequency waves, which were eventually taken up in the US for radar, these people were working together on a different device called a klystron. Now, it was a little behind the magnetron in terms of power output, and that's why it wasn't used at first in World War II in radar. But they persisted developing it because it looked like it would be an extremely useful device. And Russ and Sigurd Varian actually went off and founded a company, which some of you may have heard of. And Varian actually at first sold these devices for, say, the telecommunications industry and places like that. And where they established this company was in a little known industrial backwater near Stanford University, which is now known as Silicon Valley. Now, this is a really interesting interplay between the needs of war and industry and the needs of physicists for particle accelerators. So they start up this company, and meanwhile, Bill Hansen starts up using this powering device, the klystron, to drive and develop new types of particle accelerators that were much smaller than the ones had gone before. And you can see there him with his team with their first version of what's called a 3 gigahertz S-band linear accelerator. And he, working with the medical community and a local doctors there, actually developed these linear accelerators into devices which could be used to treat patients in radiotherapy. Now, Varian, you might not know, was actually the first IPO, the first floated company in Silicon Valley. And this activity around radar, particle accelerators, and high-tech vacuum tubes actually laid the foundation for the high-tech companies and manufacturing and expertise in the area from which Silicon Valley later grew, which was a really interesting background. So I'm giving you this example as a way to show you that physics and particle physics in particular has never been isolated from society. It's never been something that's just done in an ivory tower, purely thinking about the foundations of our universe. The people who get in their hands-on and actually build the experiments, and this type of accelerator led to the Stanford Linear Collider that eventually discovered quarks, doing this activity is part of our society, and it interplays in many different directions with industry and obviously with medicine. Now, I was researching these stories for the book that Connie mentioned I've just written in the last couple of years when I became aware of a sort of much larger story around this, because it would be easy to think that having come up with radiotherapy and then letting industry, including Varian, one of the major suppliers of radiotherapy linacs, it would be easy to think that the job of the physicist and the accelerator physicist or particle physicist, it sort of finishes there in the story. And it came as a bit of a surprise to me that our job hasn't finished. Now, one thing you might not be aware of is that these accelerators, not just the type that Bill Hansen designed, but all different types of accelerators that have been invented in many different creative ways throughout the decades, are now used in so many places in our society. So obviously medical applications is a major one, which I'll touch on more, but there's more and more accelerators also being used in industry to make the chips inside our mobile phones, for advanced manufacturing, for non-destructive testing and things like this. So they're a really, really ubiquitous technology. And one of the most commonly used ways that we use these small accelerators is to generate X-ray beams for cancer treatment. And about one in 2 patients where this treatment is available are treated using radiotherapy among successfully treated cancer cases. So it's absolutely a mainstay of cancer care worldwide. And there are now many suppliers who will sell these. There are 2 main market leaders, and they're extremely sophisticated technologies integrated with the imaging. This small particle accelerator generates electrons, turns them around, hits them onto a metal target. That generates the X-rays, which are then shaped. And everything is designed around delivering the optimal dose where it needs to be in the patient, measuring that, delivering that, and giving the patient a good quality outcome. And I was aware of this, but I guess something that I maybe wasn't aware of was the overall rate of cancer deaths worldwide. I had assumed, because I live in a high-income country, well, 2 high-income countries, the UK and Australia, that overall the rate of cancer deaths worldwide was decreasing because we've gotten better at treating cancer. And if you normalize for overall population growth, this is true. But if you look at the overall actual raw numbers, the number of cancer deaths is going up over time because more people are living longer and healthier lives. And so you're actually more likely perhaps now even to get cancer or die from cancer than you were of other diseases before. And so the cancer burden worldwide is actually increasing, not decreasing. This came as a little bit of a surprise to me, but it means that these devices or these accelerators are of even more importance in the world, as are the other ways we're learning to treat cancer, say with charged particles, which is something that I had worked on previously. What I didn't know, though, was that by 2035, about 75% of these cancer deaths worldwide are going to be in low and middle income countries, not in high income countries. And actually, if we look at the treatment facilities available, based on the estimate of needing one of these radiotherapy units per 500,000 members of population, a lot of the world is very well served already. We don't have a shortage of these machines in, say, the UK, Australia, or indeed in Switzerland. But there are parts of the world where there is no access to this treatment and a severe shortfall. In fact, we already know that we're missing about 5,000 of these machines, keeping in mind there's only 12,500 of them in the world as it is. So we need a huge ramp up in these machines. And then in about 2017, I was invited to a workshop at CERN, which was bringing together people from the Accelerator community, both at CERN and also a number of my UK colleagues. And let's just go back one. And also an international cancer NGO called the International Cancer Expert Corps, and a whole lot of stakeholders, medical doctors, oncologists, medical physicists from lower middle income countries, from many parts of sub-Saharan Africa, and also Nepal and a few other different places. And we sat in the room together, and at first I didn't even want to go to this workshop because I had only worked on proton accelerators. I hadn't worked on these small compact electron accelerators, and I didn't know what I could contribute. But I thought, okay, well, I'm interested to learn about this because this is a type of accelerator that I talk about in my science communication, but I don't know an awful lot about it. So I went purely in that instance to try and learn and speak to people and learn about this wider context of the research that I did in particle accelerators. And what happens over time when you put these interesting different communities and different nations together is this process which I now describe as becoming T-shaped researchers. Now, the classic scientist is an I-shaped researcher. They have one deep specialization usually. And what is happening more and more over time, hopefully my clicker will reveal this, there we go, is that over time when interdisciplinary collaborations spend time together, it's a bit of a journey that you have to go on. So at first, researchers from different disciplines will oscillate between asserting their own field or hanging back and sort of listening to someone from the other field. And you have to slowly gather the skills, both the listening skills, but also the actual technical skills and language in order to actually work together productively to solve a problem on an interdisciplinary scale. And this is the process that we went through. And so I found myself not just sitting there listening, but actually as a science communicator as well as a scientist, I found that my most valuable contribution in the moment at that conference was being able to put in plain language why, the frequency of the accelerator was important to the overall size, why one thing had to work the way it did and not another way. So I was able in a way to bridge the two communities because I had some background in medical related technology. But all of us over time had to go through this process. And you'll notice that the vertical axis on this process of becoming a T-shaped researcher is all about communication, right? And so it turned out that one of my most valuable skill sets that I'd been doing to the side of my research became front center and absolutely essential to the work that I was about to embark on with this collaboration. And I sat there and we listened and we heard these stories of these machines. And the problem was not just a lack of the machines, but when they're installed, they break more often. And this was a picture of Uganda's one and only radiotherapy unit at one point in time. And I don't think I need to explain from the gaffer tape around it what the problem is here. Robustness is the problem. But nobody actually had any data on how the machines were breaking. And so one of the very first projects that I did with one of my students as part of this, he went over to Nigeria and Botswana for 3 weeks, and we actually gathered the first data set to try and break down these machines in an intricate complexity and understand at a statistical level what was actually happening and what was going wrong, because this data did not exist. It was extremely difficult to get hold of. And we found that at least 6 of the subsystems fail twice as often as in the low and middle income countries compared to high income countries. And there were some subsystems like the vacuum subsystem that never had a failure in 10 years in the UK hospitals we looked at, but failed quite frequently in low and middle income countries. And so over time, it was really asking the right questions and having the right conversations that led us to do that work, and then led the group or the collaboration as a whole to form a new initiative called Stella, which is Smart Technologies to Extend Lives with Linear Accelerators. And so we've now formed this international collaboration in order to try and address this problem of the shortfall of radiotherapy machines and their robustness in these environments, to try and contribute what we can to this extremely complex interdisciplinary challenge of delivering cancer care throughout the world in an equitable way, not just in the countries that can afford it. So that's been an absolutely wonderful journey to have gone on. And this program now sits alongside a lot of my other more technical, detailed research in particle accelerators. But it's one that absolutely, I think, chimes with this idea of bringing our science and our communication and our values together that Ed Yong so nicely put in his piece this morning. And so just to finish, I thought I'll read another tiny couple of sentences from this piece, which I really recommend you read. And it comes as a reflection on the pandemic and how a lot of scientists have now realized that their work is actually can't be separated out from the rest of society, and suddenly have realized how important communication, politics, framing, all of this stuff is in the world. And he says, the pandemic clarified that science is inseparable from the rest of society, and that connection works both ways. Science touches on everything, and everything touches on science. Thank you so much for your attention. And if you're in the UK, you can already pre-order the book that tells these stories and many more, and how particle physics experiments have changed our world. But please keep an eye out for it. It will be in about 11 different languages from next year. So very much looking forward to that. And I'd love to take some questions if you have them.
Thanks a lot, Suzie, for that very interesting presentation. I feel like we've just covered the tip of the iceberg of your work, if only we had more time. And there are already quite a few questions coming up. So here we go. I see your book is entitled The Matter of Everything. You must have had many ideas for your first book. What made you choose this one?
Yeah, that's a really great question. I guess I really wanted to capture this interplay between society and particle physics, because particle physics in particular is such a curiosity-driven field, and most people think it's so esoteric, right? They don't think there's any practical applications. But to those of us working in the field, we know that these stories, we know that we know the influence it's had on society, but I felt that nobody had really tried to tell that story. The other aspect is that as an experimental physicist, I felt that all the books out there about physics were really written by theorists. And I thought, well, hang on, this isn't, theory is wonderful and it's awe-inspiring, and these books are amazing, but it doesn't tell anybody how you actually do this, how you actually walk into a lab, build an experiment, and interact with the world on a scale that is too small for us to see or touch or even know that it's there. And that's really what I do. And so over time, it became clear that that was the story I needed to tell, this sort of large sweep through these 12 selected experiments, and how they've come to influence our world, but over long timescales, much longer than most politicians or even business people are used to working with. And I think now one of the interesting things that's happening is when I proposed this book, we didn't have a global pandemic. We didn't see these things that Ed Yong is pointing out about how integral science is to our society and the long-termist approach we need to take to that. And I think this book really tells the story of that in physics at this very fundamental level. And so I think that's part of the reason why I'm so excited about it and why I'm getting a lot of interest from people about how this works really in the real world. So it became a story I had to tell.
You say that people physicists aren't really telling the story of how the process of creating an experiment. And I think back to the old days when we did live festivals 2 years ago. It seems so long ago. And our science pavilions at music festivals, one of the most popular items on the program is the build your own cloud chamber. And that just, is basically a fish tank with some dry ice and some wonderful volunteers, but it is an actual little experiment. And I've had people leave that workshop in tears because they've been moved by the whole process and what they've seen, and it's amazing, yeah. Another question along the same lines on outreach, which is interesting because I've been in a debate on this topic as well. There are those that say all physicists should be obliged to do some outreach. What do you think of that?
I think there are different types of scientists, right? So just as I would say there are some I-shaped scientists and some T-shaped scientists where you have a deep specialization and a breadth to what you do, there are different types of scientists in terms of there are the politician scientists, there are the deep theoretical scientists who struggle to even explain to their colleagues exactly what it is they're doing. And then there are the sort of communicator scientists. I think I would put myself in that category. Obviously, you're doing science, but your skill set lends itself to certain other activities, right? So I would not force people to do public engagement. In fact, there are studies that have shown that poor public engagement is worse than none in terms of the impact that it makes. And we do need to think about how people feel when they engage with science. And that takes time and energy and skill and a desire to do communication and public engagement well. So no, I'm not a fan of forcing people to do public engagement. Of course, a lot of people maybe think they can't communicate what they're doing because it's too complex. And I would challenge those people to try and think about distilling down their ideas or presenting it in a way that people can engage with. We do, as a community, I think, have a mandate to communicate what we're doing to the public who pay for it. But I think that's kind of a very, narrow way to look at science communication when you consider it as a part of culture and a part of society. There is a demand there from people to know the kinds of things that inspire us as well about the nature of the universe and how the world works. And people should be able to access that regardless of their mathematical background, in my opinion. So there's many roles that people can play, and there's also presenting like I do, for example, or writing are only two examples of the ways you can communicate science. Even having a good conversation over a dinner table with people who are interested in what you do counts. It has an impact.
Yeah. I'm really hoping that we'll have the opportunity to welcome you at one of our science pavilions with the book once it's out. That would be absolutely amazing. So a different question here, addressing the lack of cancer treatment machines in certain poor countries. Now, you mentioned the Stella Project that you're collaborating on. In perhaps more layman's terms, in everyday actions, is there anything being done to address it? Can we support particular charities, for example, this person's asking?
Thank you. That's a wonderful question. Yes, if you'd like to support the project, I recommend you look up the International Cancer Expert Corps, ICEC. They're an international NGO, and if you want to work with them or talk to them or contribute to them, that will go directly into trying to solve this challenge.
Could you say that again, Suzie? ICEC, just so that we get that one right.
C. International Cancer Expert Corps, ICEC.
Okay, got that one. Which type of accelerators has the best future? In the radiotherapy domain, antiprotons?
Oh, that's interesting. As in which type of machine, I think is kind of the question. Again, it depends if you're looking on the short term or the long term. I mean, in the short term, these existing types of radio frequency accelerators, while they may be slowly moving to higher frequencies and getting a little bit more compact, in the shorter term, those are extremely effective. In the longer term, of course, we may get a breakthrough that gives us a completely different paradigm of cancer treatment, or a completely different paradigm of accelerating particles, like, say, plasma acceleration or laser wave field acceleration. So in the long term, I hope cancer treatment will look different in 20 years from how it looks now. I hope it will be a lot easier, that the technology will be a lot smaller. Maybe we'll find a way that doesn't even require particle accelerators or radiation. I don't know. But at the moment, certainly at the moment, and over the last 5 to 7 decades, radiotherapy and radiation has been an absolutely integral part of cancer treatment and the solution to the cancer burden worldwide. So I would say for a while this is still going to play a role, but I couldn't tell you exactly which type of technology is going to dominate in the future, because I think there's many options on the table. I hope that sort of answers the question.
I hope, I guess so. I mean, but listening to you also, these machines are still extremely expensive, of course.
So the ones we have are relatively inexpensive now because they've been industrialized, but to buy one of these radiotherapy machines still cost a couple of million of whichever currency, or a couple of million Swiss francs, a couple of million pounds.
Right, which leads us on. We've only got 30 seconds left. I'm going to have to just pick. What are the next steps for the data collected from Africa?
Yeah, so I've actually already expanded the study to a study across Indonesia as well, and the paper on that one is about to come out. And then we're looking to expand that into a more automated system of data collection, and that's something that we're talking to vendors and data scientists about. So if you're interested in that, please do drop me a line if that's something you can help with.
Suzie, thank you so much for your time again, for giving up your Sunday afternoon. It's a pleasure listening to you, and I can't wait till we meet again in person. All the best.
Thanks so much, Connie.